So welcome to everyone to this first lecture, which is going to be on the subject of SpinDynamica, which is a program in Mathematica which until recently I've been programming by myself. And essentially it's a system to perform simulations and theory of NMR within a Mathematica environment. And for those of you who want to use this program, then you can download it from this website here. And there is documentation and examples of how to use it there. First of all, point out that we've now, after many years, finally published an article on SpinDynamica with my student Christian Bengs, which you might want to have a look at when opportunity arises. That will give you a little bit more detail on how the program is constructed and more detailed information on what you can do with it. I'll mention that the history of this program for some time. So this started out when I was writing my book, and I started to generate myself some simple Mathematica programs in order to help check my own calculations. And since then it grew through a long period, essentially as a side project by myself. But recently my student Christian Bengs has been helping me with that and also starting to program himself a lot of modules which are badly needed. And it looks right now as if the functionality of SpinDynamica is going to expand a lot, reasonably rapidly now. Now, it's within the environment of Mathematica, which has both advantages and disadvantages. The main advantages are that Mathematica is highly platform independent. So once you learn to use SpinDynamica on some platform, then it will work on virtually any computer, including supercomputers, without any modification at all. It gives you access to a very high-level graphics and numerical routines of Mathematica and symbolic algebra of a very high and general nature, which are very useful for magnetic resonance, in fact. When one puts in the work to develop a program, you don't really want that program to be reliant on you yourself for it to continue to exist into the future. And in fact, many very good NMR simulation programs have suffered from the fact that at some point, nobody's there to maintain them anymore. But by using the Mathematica environment, then that's reasonably well future-proofed, actually. And the philosophy of Mathematica, which is a little bit special, which is based on many matching and manipulation of patterns, turns out to be rather well suited to what we do in magnetic resonance and how we think about experiments. But there are disadvantages, of course. The main disadvantage is that it is commercial software and you need to have a license to run it. And there's not much I can do about that. It was just a choice made very early on. Perhaps a good one, perhaps not a good one. Mathematica itself is not the easiest program in the world to learn. Those of you who are not familiar with it, have a go at it, might find that you have quite a bit of a curve to get through in the first few weeks. Another disadvantage, which becomes more apparent when you do programming in it, is that the code you generate is sometimes very hard to read, even for yourself after a few weeks, actually, just because it's so concise. In some cases, it comes with a speed penalty. It's usually that if you have something which is more general, then usually you have to trade off some speed, and that's true here as well. And for those of you who get into magnetic resonance and want to simulate experiments, you might well have some specific tools for your particular experiments which are faster. But they're probably not going to be more general than this. So you may also yourself have to choose that. The ambitions of SpinDynamica are that it should be platform independent, and as I said, that's rather well fulfilled just by using the Mathematica platform. There's a very ambitious remit, really, to try and cover everything that we do in magnetic resonance. And that's only partly fulfilled right now. And there's some important domains of magnetic resonance which are not covered yet by SpinDynamica, but which will be, some of which will be done quite soon. And I think as I explain more about the program, then you'll maybe see how general it is. I'll just mention some things which are currently under development, which are currently missing, not fully implemented. Maybe a very important one actually is chemical exchange, which I know that Art will cover in some of his lectures, and is a very important part of modern magnetic resonance. And at the moment that's not part of SpinDynamica functionality, but it's being implemented as we speak actually. And at the moment SpinDynamica is rather weak on multidimensional spectroscopy and in covering phenomena such as flow and diffusion. But again, these are things which are likely to develop in the future. Now, what most people, in my experience, like about SpinDynamica, in a way is a bit paradoxical, is that it's not a black box, in the sense that you have to do quite a bit of work yourself, usually, to implement a particular NMR experiment, which in one sense is a bit of a nuisance in the sense that it's not usually just ready to plug in and do what you want. But it also has the advantage that you really understand what you're doing when you implement a SpinDynamica implementation. And we'll cover right now the basics of spin systems and so on. So one of the main ambitions here is that by using SpinDynamica, it helps you understand how magnetic resonance works, rather than just being a program which has been designed by somebody else and which does a specific task. You actually have to understand, not only do you have to understand what you're doing, but you also, implementing SpinDynamica actually assists you in understanding your experiment. Having said that, there are a small number of powerful routines implemented which let you do some very common tasks very quickly, and I hope to be able to demonstrate some of those during the week. It's completely open source, so the code for SpinDynamica is distributed and is readable and usable by anybody, except they will need a mathematical license to actually run it. Okay, let me say a few things about how SpinDynamica is organized. Let me expand this a little bit. So it's not one single program, it's a whole assembly of different Mathematica programs which interact with each other and call each other as they're needed without user intervention. So in particular, and what we'll be talking about mainly today, is its quantum mechanics modules for defining magnetic resonance problems in terms of quantum mechanics and setting that up for you. And then probably tomorrow I will be talking more about the spin dynamics modules for actually deriving how spin systems evolve in time and solving that, and some specific simulation tasks which are set up in the structure of SpinDynamica. The quantum mechanics modules are themselves organized into modules which use something called either Hilbert space or Liouville space, and I'll be trying to explain to you what those things are. And the defining objects in these two types of spaces are called operators and superoperators. Now, superoperators are objects which tend to have been a little bit neglected in the way we often talk about magnetic resonance. It's maybe for people who are just starting in magnetic resonance, the thought of handling superoperators maybe seems a little bit intimidating. What I'll try to do is to try to convince you that actually the language of superoperators is rather natural and there's nothing particularly difficult about it. But that's an ambition which we'll see how that goes. Then we'll have the modules which are involved in calculating nuclear spin dynamics. And they're organized roughly as shown here. What I'll be talking about mainly in this course are objects which I call generators, which are the way of defining what derives the evolution of nuclear spins. And there's basically two types here, spin Hamiltonians and relaxation superoperators. And we're going to be looking at how these two terms, how they're defined and how they work. When we do an NMR pulse sequence, we're often doing a sequence of events in time. So there has to be a language of defining those events and transmitting that to the computer. So I'll be explaining how events are constructed in SpinDynamica. And then there are packages for doing particular simulation tasks in SpinDynamica. For example, simulating the NMR spectrum, which is the task of this routine called Signal 1D, or for simulating the trajectories of particular observables in time. That's a very useful one. Or simulating how a particular pulse sequence performs a certain task of converting one mode of spin order into another mode of spin order. That's the task of a routine called transformation amplitude. And one aspect of SpinDynamica which I think is very powerful is a facility called ensemble average, which allows one to average NMR simulations over particular parameters. And that's done in a very general way, so this is not specific. As you'll see, this allows one to deploy powerful Mathematica routines, such as sampling of distributions within a spin-dynamical context, something which I know that many other simulation programs in magnetic resonance don't really do. They may set up some particular types of computation for some specific tasks, but this lets you do sample distributions in a completely general way, something which I suspect is actually very important for interpretation of many NMR data in complex systems. So that may be something which those of you who work with conformational distributions or something like that might want to pay some attention to. Okay, so let's get started. If you download SpinDynamica, then you need to follow the instructions of just how to set that up. You download the package from the SpinDynamica website. As explained in the documentation, you have to tell your computer where the SpinDynamica directory is. There's a particular way of doing that, which I'm not going to cover because that's in the documentation. Having told the computer where SpinDynamica is, you can then load it, which is done through this this routine here. Needs is a Mathematica instruction which calls in a package if it's not already been loaded. So here I've just started Mathematica actually, and I just load SpinDynamica, and it gives a message saying that the latest version, which happens to be this particular one, has been loaded, and gives some other information which I'm not going to worry about right now. The next thing which one can do now is to define the spin system which are going to be used in the computations. And that's done with a SpinDynamica routine called setSpin system. And we'll use here, just to get started, I'm just going to study the properties of single spin a half. So by executing setSpin system 1, then it actually defaults to a spin system which, without explaining exactly what this means, can go into that later. This means it set up a single spin system containing one single spin with quantum number 1/2, and the label of that spin is number 1. And it also sets up a basis in which SpinDynamica is going to start working, and I'm going to be talking a bit about what that means. We'll be looking at different spin systems as well. So right now we're in an environment where we're looking at a single spin 1/2, and that's the way one needs to start discussion of magnetic resonance. So, right, so we have a single spin 1/2. And the first thing we have to do is to get to know the world of a spin 1/2. The world of a spin 1/2 is governed by two spin states, which in magnetic resonance terminology are called ket alpha and ket beta. Alpha and beta refer to the angular momentum in a particular direction, which by default refers to an axis system in which ket alpha is a spin state with angular momentum of 1/2 unit along the z-axis of the axis system, while ket beta has angular momentum of -1/2 unit along the same z-axis. Now, if we want to write that mathematically, we would write something like this, that the angular momentum operator along the z-axis, when acting on the state alpha, generates angular momentum of +1/2 along the same axis. So what we've drawn here is something called an Eigen equation, that an operator acting on a state generates the state back again multiplied by an eigenvalue. So that's called the eigenvalue of angular momentum along the z-axis as being +1/2 unit. Similarly, the state beta obeys an Eigen equation in which the eigenvalue is -1/2. So this is the world of a spin 1/2 particle, such as a proton or a carbon-13, or an electron for that matter. There are two states, alpha and beta, which obey this particular Eigen equation. These are two Eigen equations. So let's just see how SpinDynamica handles that. So the world of a spin 1/2 can be described using a basis. And in this case, this world described using these two states, alpha and beta, is called the Zeeman basis. And objects such as operators are written as matrices in that basis. Now, SpinDynamica by itself defaults without intervention to the Zeeman basis. So let me just edit this and execute something. So we set the spin system to 1/2, and then we can ask SpinDynamica what its basis is right now. And it says it's the Zeeman basis for this spin system, consisting of a single spin with quantum number 1/2. And the 1 here, it means the label of what the spin is called. It's called spin number 1. And we can ask SpinDynamica what are its kets for that basis. and you see that the kets are these two states, alpha and beta. Now in quantum mechanics you have two sorts of ways of defining a state. You have what's called the kets and you have what are called the bras, which are written using the opposite notation. So the basis kets are ket alpha and ket beta, and the basis bras are written using this notation was introduced by Dirac. And Dirac introduced a quantity called a bracket, which is where the term bra and ket comes from. That if you take the bracket between two states, you get 0. If the states are different, but if the states are the same, you get 1. And in fact, all the kets in a basis have this property that the bracket between different states is 0, and the bracket between the same states are 1. And such a basis has the property of being called orthonormal. We can write that mathematically by saying that the bracket between state I and state j is equal to a symbol called delta function, where this has the property of being 0 if I is not equal to j, and 1 if I equals j. And one of the tasks in quantum mechanics is to set up a basis of states which have this orthonormal property. So for example, the first ket in the basis here is ket alpha. The first bra in the basis is bra alpha. And if we take the bracket bra between the first bra and the first ket, we get 1. But if we take the bracket between the first bra and the second ket, we get 0. So that's orthonormality. Okay? If instead we have a system of 2 spins a half, now I've set the spin system to 2 spins a half, called 1 and 2, but both with spin a half. Then there are now 4 basis kets, which are given by these states here. So the second ket now is beta alpha, and similarly the third bra here is bra alpha beta. So we can execute these brackets between different kets and bras in the system of 2 spins a half. So SpinDynamica sets up by default the Zeeman basis of these bras and kets for whichever spin system one's interested in handling. There are other bases that one can explore as well, but I think I'll defer that topic to later in the course. Now let's look at spin operators. So we've already seen one of the most important sets of one of the most important spin operators in magnetic resonance, which is called IZ. which is the operator for the spin angular momentum along the z-axis. And of course there are three similar spin operators which represent angular momenta along the three orthogonal axes. And a great deal of NMR theory is concerned with the property of these operators. The three operators have a relationship based on their mutual commutation, or what's called cyclic commutation, which is this property. This construction here is called a commutator. The symbol with square brackets and a comma is another way of writing the product of the two operators written in two different orders and subtracted from each other like that. That's the definition of a commutator. Operators are objects where it matters which order they're applied in. So in general, these two products of operators, Ix times Iy and Iy times Ix, will be different. The angular momentum operators have the property that the commutator of Ix with Iy generates Iz multiplied by the complex number square root of -1. And this relationship can be cyclically permuted. So one often writes a symbol of this kind. Cyclic permutation, which means that you can cycle around the three operators as you want. So as well as Ix, commuter Iy goes to Iz, you can cycle around, make y go to z, so then I would have Iz cyclically commuting with Ix going to Iy, and then you can go one step more, starting with Iy, commutator with Iz would then give Ix. So these are three very important operators for the angular momentum along the three Cartesian axes, x, y, and z. And a great deal of NMR theory is built upon these operators. One can use those operators to define some other important operators which also come into NMR theory. So, for example, there's what's called a shift-up operator, which is Ix plus I times Iy. And there's the shift-down operator, Ix minus Iy. Now, in SpinDynamica, the functionality of these operators is contained in a symbol which has the name op_i. The name capital I would be useful, but that's reserved in Mathematica for the square root of -1, so that couldn't be used. So the symbol op_i's has been used instead. So let's see how that works. So for example, let's look at a system of 3 spins a half. So now I set the spin system to 3 spin half particles. And we can define some spin operators. So So here I've used the symbol op I and given it some arguments inside the square brackets here. The first argument says which spin this operator belongs to. So in this case it's spin number 1, and it's a Z operator. So this is the operator I1Z for the angular momentum of spin number 1 along the Z-axis. Similarly, one can define the shift operator for spin number 1, or the Y operator for spin number 2. Now there's a bit more functionality as well. So let's think we have an axis system again, X, Y, Z. We may have angular momentum along the x-axis. That's defined by the operator Ix, or along the y-axis. But suppose that we're interested in the angular momentum of spins at some other axis. For example, it may be in the direction in the xy plane, but at an angle of phi from the x-axis. So this would be Ix cos phi plus Iy sin phi. That would be the operator for angular momentum in that direction. And SpinDynamica knows how to construct things like that. In SpinDynamica, that's done by asking for the angular momentum at some phase angle. So for example, in this case, we have the angular momentum for spin number 3 at some particular symbolic angle in the xy plane. So those are operators which are sometimes needed, and here you start to see that Mathematica works symbolically. It doesn't require that you give numerical values for these symbols, and indeed one of the more attractive features of SpinDynamica is that it lets you do symbolic calculations, not just numerical calculations. More generally, we might have angular momentum. So that example had the angular momentum was at some strange angle, but still in the xy plane. But we might be interested in angular momentum at some arbitrary direction in three-dimensional space. So with a polar angle phi and then a phase angle phi. That would be described by angular momentum of this type, that you would have Iz cos theta plus Ix cos phi plus Iy sin phi sin theta. That would be angular momentum in some arbitrary direction in three-dimensional space. And SpinDynamica can handle that sort of thing too. Here the syntax would be using these two polar angles. Okay. So an example here is shown by executing this line here. And we see the symbolic form of that angular momentum. Now let's look a bit more at the functionality of op-I. Very often we're not interested just in the angular momentum of a single spin, but of several spins at the same time. So in this case, I've asked SpinDynamica for the angular momentum along the z-axis for two spins which are in the same spin system, called spin 1 and spin 2. And then we get the sum of those two angular momenta. And in fact, if we don't specify anything for which spin we're talking about, we get the sum over all of the spins in the system. So at the moment we have a 3-spin system. We could check where we are actually, what spin system we're handling with at the moment, just by asking SpinDynamica to tell us which spin system is currently active. In this case, it's a system of 3 spins a half. And then the op I acting on Z gives the total angular momentum along the Z-axis, which involves all 3 spins. And that also goes for the angular momentum at this particular direction in the XY plane. So this is also part of the functionality of this symbol op I. And another important part of the functionality is involved when we get to the topic of defining spin Hamiltonians. A very important term in a spin Hamiltonian may be written something like this, which is the scalar product of 2 angular momenta. This quantity I1 dot I2 is involved in the definition of J-coupling Hamiltonian in solution NMR. So we'll be using that when we get onto that, problems which involve J-couplings, as most problems in solution NMR do. The dot product between 2 angular momenta, like that, is defined as the product of the x angular momenta plus the product of the y angular momenta and the product of the z angular momenta. And in SpinDynamica language, that's constructed just by taking the dot product of 2 op I symbols, as shown here. So the evaluation of the scalar product gives, exactly as written, the products of the x angular momenta plus the y plus the z. So what I've been talking about now so far is the definition of operators. What can one do with those operators then? So we had an example of that already. That if we have a single spin system, that when we apply the z angular momentum operator to the state alpha, we should get the state alpha back again multiplied by its eigenvalue, which is plus 1/2. So SpinDynamica knows how to do that. So let's make sure our spin system goes back to a single spin half. The first ket in the Zeeman basis is just ket alpha. So if I take Iz and apply it to ket alpha, then the answer is a half ket alpha. So that corresponds to the equation over here. Similarly, if I apply Iz to ket beta, which is the second ket in the basis, then I get ket beta back again, but with eigenvalue of minus 1/2. And that's what's been done here. So ket number 2 in the basis is ket beta. So ket 2 is beta, and applying Iz to ket beta gives minus ket beta over 2. What happens if I apply the shift up operator? to beta, it shifts ket beta up into ket alpha. That's why it's called the shift up operator. And of course SpinDynamica knows about that too. So here I've applied the shift up operator I plus to ket beta, and the result is ket alpha. So SpinDynamica knows how to do all of those manipulations. We can try to do something which is maybe a bit risky, because I'm not sure exactly what the answer should be. What happens if one takes the angular momentum operator in an arbitrary direction So this would be the angular momentum operator in the direction defined by two polar angles, and applies that to ket alpha. I have to confess that I don't know what the answer is, so let's see if SpinDynamica can tell me. And indeed it can. And this maybe starts to show a little bit of the power of it, in that there are many results which are very hard actually to derive analytically by pen and paper, which SpinDynamica can do immediately. Now you can also multiply operators together. We've already seen a bit of that. So many of you who have done some NMR theory will start to be familiar, I think, with operators which are products of angular momentum operators for different spins. In SpinDynamica, such operators are constructed using the dot construction. So if I make sure that we're using a spin system of 3 spins a half, for example, and now I can take the product of x and y for spin 1 and spin number 3. Incidentally, if I define that product the other way around, so 3y dot 1x, the result is the same. So SpinDynamica knows that operators belonging to different spins commute with each other. So therefore the operator belonging to spin number 1 here can be legally placed in front of the operator for spin number 3, and it doesn't matter. So SpinDynamica knows about that, but it also knows that if the spins are of the same type, then the operators should not be. The operators are different, depending on which order they have. So SpinDynamica does not rearrange such products. So there's some built-in intelligence, if you like, in the SpinDynamica routines, which are done without us having to think about them. Notice that to multiply operators in SpinDynamica, one uses a dot symbol. If, for example, one tries to multiply 2 operators using a times, this should generate an informative error message. So SpinDynamica, for the most part, will give reasonably informative error messages when the syntax is not correct. Which spin system am I in right now? Okay, 3 spins a half. So this construction of the product of 3 operators, one notices that SpinDynamica has automatically placed them in order of the spins involved. Okay, so that covers the pretty much the field of the op-I routine, which defines angular momentum operators, and which is involved in a great deal of NMR theory. Now there are some other operators involved as well, which can be just briefly reviewed here. There are rotation operators, which are important in spin dynamics for defining the actions of pulses, for example, on spin systems. And the functionality of that is governed by the op-R routine. So, for example, here I've gone back to a single spin half. This is the rotation operator for a rotation through the angle of pi over 2, that means 90 degrees, about the x-axis. For a rotation through the angle pi about the x-axis. And we could apply that to a spin, for example, ket alpha. So let's think about what we're doing here. So suppose we have ket alpha, a spin which is has angular momentum along the z-axis, and now we rotate it by pi around the x-axis. The result is a spin which is now has angular momentum along the minus z-axis, ket beta. So let's just try that, and it's going to be a little bit instructive actually. So here again, I'm now applying this rotation operator for a rotation through pi around the x-axis to a spin in state ket alpha. And indeed we get ket beta. Now we also, though, get a phase factor, which tends to surprise a lot of people. And this is not an artifact of the Mathematica or something, this is mathematically correct. And I won't comment on it further except to say that a 180 degree pulse converts alpha to beta. It does convert alpha to beta, but with an additional phase factor of minus I, the square root of minus 1. And there are occasional NMR experiments where that sort of thing is important. If we rotate about the y-axis, then actually we get just ket beta. Now we can do such manipulations also in multiple spin systems. So if we have a 3-spin system, and here I've set up to ask what happens if you apply a 90 degree rotation around the x-axis to a 3-spin system which is in state ket alpha alpha beta. And again, this is a computation where I couldn't say precisely what the answer is. And the answer turns out to be rather complex. It's a mixture of many different spin states in the 3-spin system multiplied by all sorts of complex factors. We could also do that symbolically using a particular angular rotation around an axis which is at an angle phi with respect to the x-axis. So this would be, by analogy with what was discussed before, we have the xy plane, we define an axis which is at an angle phi, and then rotate by pi over 2 in this case, around that particular axis. That's the sort of thing one would do with a 90 degree pulse, but with a phase shift of phi. So that phi there would be a phase shift. So we start to get a bit closer now to what one really does in NMR experiments. And here we're acting on a particular spin state, alpha alpha beta, a state, one of the possible spin states for 3 spins a half. And again, the result is probably complicated and rather difficult to derive oneself. involving complex exponentials and so on. Mathematica is good at manipulating these things. So we could, if we don't like complex exponentials, e to the I phi type constructions, we can take the result of the last computation and apply conversion from exponential factors to trigonometric factors. And then we get cosines and sines instead of exponentials. And we could also ask Mathematica to have a go at simplifying that. So it puts it in a rather simpler form. And then Mathematica finds some rather useful factorization of that expression. So this is the sort of thing that Mathematica is very good at and which helps us in spin dynamical computations. Now there's another class of operators which come in later this week. They're involved a lot in the theory of solid-state NMR and in relaxation theory, called spherical tensor operators. SpinDynamica has definitions for spherical tensor operators, in fact arbitrary spherical tensor operators. The one which is the most useful and most frequently encountered in NMR theory is called the spherical tensor operator, opt, of rank 2. And I think I'll spend a little time later this week talking about spherical tensor operators. The spherical tensor operator of rank 2 has actually 5 components, with another quantum number, usually called m, which takes values from -2 to 2. So there are actually 5 operators of that kind, and SpinDynamica knows what they are. We're going to come back to spherical tensor operators because they're used heavily in relaxation theory. Now let's just look briefly at some of the things we can do with operators. I think I'm going to look first at matrix representations of operators. So the way this goes is you can express any operator as a matrix. The dimensions of this matrix depend on which basis one has. So the dimensions are the basis states. So for example, if we have 2 spins a half, we may have a Zeeman basis in which we have a set of basis states of this type. The columns of the matrix are labeled by the kets, and the rows of the matrix are labeled by the bras. And each element of a matrix, so let's say this one here, corresponds to a particular bracket of an operator between the corresponding bra and the corresponding ket, which would be this in this case. And then one fills the matrix with all of these different brackets. That's called a matrix representation of an operator. And SpinDynamica calculates these matrix representations. So first of all, let's just look at what happens for a single spin a half. The basis kets and bras we are dealing with are just alpha, beta. And one can ask for the matrix representation of any particular operator. So let's look, for example, at the Z operator. When this is executed in SpinDynamica, the result we get doesn't look maybe as expected. It doesn't look in the form of a matrix. SpinDynamica uses what's called sparse array representations of matrices, which is a particular way of storing a matrix which uses minimum amounts of memory. So to actually look and see what the matrix representation looks like, we have to apply another function to that, which is called matrix form, to actually examine the matrix representation in a visible way. In fact, there are different ways in Mathematica of representing matrices. So a convenient one may be matrix plot instead of matrix form, which gives a sort of graphical representation of the matrix. And that can be very useful for looking at large matrices. So, for example, if we let's, for example, say we have a 5-spin-a-half system. We now would have a large number of basis kets. But we can look at a particular operator. So this would be the product of I1x, I3x, I2z. One gets a large matrix with many elements. Most of them are 0 actually in this case. But we could also look at it as in a graphical form, which makes us helps us see much more naturally the structure of the matrix. The same goes for rotation operators. So this monstrous thing here is now the matrix representation of a rotation by 90 degrees around the x-axis for 5 spins a half. Or similarly, here we're looking at the rotation around around a particular angle. This would be a rotation through the angle beta, left symbolic, about an axis with phase phi. And we get this sort of huge matrix here with all sorts of trigonometric terms in. And those of you who know some familiarity with NMR theory may know about this type of expression as being important in cozy experiments, in which a great deal of analysis is done on these particular flip angle dependencies of coherence processes. And it's all done extremely quickly in SpinDynamica. Here's another one. Here, here I'm interested in an operator. What I've done here is I have a product operator, I1x, I2y, but I've taken the complex exponential of it. So the exponential of an operator given by minus I is the square root of minus 1, multiplied by some phase angle times this product operator. Now it turns out that this sort of thing would be, comes into spin dynamical theory as the evolution under a spin-spin coupling. This is the operator for how the spin evolves under a particular product operator in a spin Hamiltonian. Something, again, not easy to calculate by hand, and Mathematica generates this type of expression very simply, involving all of these trigonometric features. So it allows one to calculate these things analytically, not necessarily numerically if you don't want to. Very useful for designing NMR experiments. And I think the final example there, something which is not easy at all to calculate oneself. This would be the evolution. So here again I have the complex exponential, that means an evolution operator, under evolution under a particular Hamiltonian, which is now the scalar coupling between two spins. That's actually, for those of you who've done some spin dynamical theory, like myself, I recognize that that's hard. I'm not sure how to do that. But SpinDynamica does know how to do it and provides the answer, again, in general analytical form. If we don't like the complex exponentials, then again we can convert to trigonometric functions, as shown here. Now, a few more operator routines. There's a very useful routine here called operator amplitude. What that is about is the following problem. Suppose we have, in NMR, when we start to look into the spin dynamics, we express the state of a spin ensemble, that means a large number of spin systems, by an object which is called a density operator. That's the quantum mechanical object for the state of the spin ensemble. And in general, it will be a mixture of many different operators with different numerical coefficients. And so on. Now, a very common task we have when understanding and designing spin dynamical experiments is we have some particular operator and we'd like to know how much of a certain other operator is inside it. Let me give an example of that. If I take I1x, I2x. Suppose I've decided that there's a term I1x, I2x. And I want to know how much of a double quantum term is in that operator. In this case, it's rather simple, but in more complex cases, it's not so easy. The way I would do this by hand is as follows. I express I1x as the sum of two shift operators, and I know from experience that Ix is given by a half I1 plus I1 minus, and the same for I2 plus I2 minus. And then I could expand that out, and if I'm interested in the I1 plus I2 plus parts, I could write that as I1 plus I2 plus, and then I would have lots of other terms in it. So I know that inside I1x, I2x, there sits an I1 plus I2 plus operator multiplied by a quarter. But in more complicated situations, it may not be very easy to figure out what this factor is. So SpinDynamica provides a routine for determining that sort of thing. It's called operator amplitude. By the way, all of these commands, you can get some documentation on them by using the question mark, which generates a usage symbol for them. So this gives the usage symbol for the operator amplitude routine. An example is easier. So in this case, I would say if I have the operator I1x, I2x, I write an arrow and ask which operator I'm interested in figuring out how much of it is in there. In this case, the example I just gave is I1 plus, I2 plus. And it tells me as being a quarter. But it's easy to construct examples which are much harder than that. Spin system. Right now I'm in 5 spins a half, so let's suppose I have I1x, I2 with some phase factor I3Z or something, and I want to know how much triple quantum operator is in that. I just ask operator amplitude to work out how much of the product of all the plus operators is in that. And in fact it's 0 in this case. I should have known it. So let's try making this a phase factor as well. And now I get some particular trigonometric function in there. Useful and not at all easy to do by hand. This was another example here of the amount of a 0 quantum operator, I1 plus, I2 minus, inside an XY operator. And finally, let's look at coherence order. Coherence order lets you know, as one develops spin dynamical theory, one finds that it's very important to know the coherence order defines the rotation properties of operators around the z-axis and is involved a lot in NMR theory, for example, the properties of phase shifts and so on. So if we take the product of 3 operators, I1 plus, I2 plus, I3 plus, the coherence order of that operator is 3. If one of them is minus, then the coherence order should be 1, because the plus cancels out the minus and leaving just a single plus as being 1. And if we take some operator which involves I1 plus multiplied by I2x, I3y, the answer in this case is that it contains actually several coherence orders, -1, +1, and 3. Those of us who are involved in designing NMR experiments know that this is quite a useful thing to be able to derive simply.